Okay, so welcome everyone to the first edition of our new Mathphys seminar series. So let me just say a few words about what it is. So this is an initiative of mathematicians and string theorists at ICTS. And this will be like a series of seminars at the intersection of mathematics and theoretical physics. So just to be clear, it's a separate series from the ICTS string seminar series. Which has its own mailing list. So please subscribe if you want to receive an announcement for this. And for the first few weeks, we're going to send an announcement to both lists. So please forgive us for the spam. And even though it's a separate series, like once in a month, we'll have joint seminars between this Mathphys series and the string seminar series for talks which are of interest to both. And so actually today, we're very happy to have our first joint seminars by Eric Sharpe. So Eric will give us an introduction to decomposition. So please, Eric, take it away.
All right. Well, thank you very much. It's a pleasure to speak here and an honor to be the first person to speak in this particular series. So I'm going to be talking about a couple of things today, really. So in broad brushstrokes, I'm going to be giving an introduction to decomposition, which I've been working on for quite a while, as you can see from the heft numbers listed there. So that will be roughly the first half of this talk. And then my plan in the second half is to specialize to a particular application of decomposition to anomalies in orbifolds. So let me begin by saying, what is decomposition? So briefly, decomposition is the observation that some quantum field theories that you might have thought were just single quantum field theories are secretly equivalent to sums or disjoint unions of multiple quantum field theories, which in this context are known as universes. So when this happens, we say that the original field theory decomposes into its constituent field theories, and then decomposition can be applied to give insight into its properties. So what does it mean for one field theory to be a sum or disjoint union of other quantum field theories? Well, one thing it means is that the theory contains projection operators. So these are going to be topological local operators that square to themselves, that are orthogonal in the sense that the product of any two projectors is zero, and that form a complete set in the sense that they sum to the identity. Then given a complete set of these topological projection operators, it's easy to argue, formally at least, that correlation functions are really a sum of correlation functions in the constituent universes. So here I've started with a correlation function in the original amalgamated theory. Here I insert the identity. So I just insert a sum over projection operators. I then use the fact that these operators are topological and that they square to themselves to take that one projector and turn it into multiple projectors hitting every one of these observables. And then this result is the same thing as the sum over the constituent quantum field theories of a correlation function computed in each of the constituent field theories, where each of these O twiddles is the projection of one of these O's into the ith constituent quantum field theory. Now that's a fine thing abstractly. As a practical matter, in order to do computations, in order to get really interesting consistency checks, we're going to need a bit more. And so something else I'm going to be relying on extensively in this talk will be a computation of partition functions. So in broad brushstrokes, a partition function is a sum over states of the theory weighted by the Hamiltonian, like so. Now, if the theory is really a sum or disjoint union, then the state space, the Fock space of the whole theory, is a direct sum of the state spaces of all of the constituent theories. Any given state in the original theory can be written as a piece from this theory, a piece from that theory, a piece from that theory, and so forth, which means the sum over states of the original theory is equivalent to a sum over blocks, a sum over universes, and then a sum within each universe of a similar weighted sum. So in particular, the partition function of the original theory is a sum of the partition functions of the constituent quantum field theories. And again, as a practical matter, later in this talk, we're going to use this as a computational tool to check and gain some insight into how decomposition works.
Sorry, can I just ask a small question?
Please do.
So maybe you'll address this soon, but when you said you want the Hilbert space to be a direct sum of individual Hilbert spaces, does that mean that
formally
there are multiple vacuum states?
Yes.
Okay.
And there are going to be lots of fun subtleties associated with that. There's going to be an issue with cluster decomposition I'm going to come back to at multiple different times. But yes, that's one of the standard issues you run into when you have a disjoint union. That's exactly right. Another issue that arises a lot is that this structure implies the presence of a higher form symmetry, which I'll come back to in a couple of minutes. So first, though, go for it.
Could you go back to the slide? Yeah. So when you are saying that the pi's, the projection operators, they become multiple projection operators, you're essentially using the expression pi I, pi j equals delta ij, pi j, right?
Yep.
Yeah. So, but then you would have to assume that the projection operators commute through the operators.
Yes. So we'll see this in examples. And in fact, the second half of this talk is going to be devoted to orbifolds, where I'm going to see very explicitly, where we can compute very explicitly these projection operators and verify their properties. But yeah, that all sounds right. I should have listed that. I should have listed that as a property, but finite time, only so much space in the slide. Yeah.
Okay, thanks.
See. Right, so let me take a minute to distinguish decomposition from something that may sound very similar, which is some aspects of spontaneous symmetry breaking. Specifically, let me take a minute to distinguish universes from superselection sectors. Now, for this audience, I doubt I need to walk through this, but in case there are young people in the audience, forgive me if I spend a minute just outlining the way I think about superselection sectors and how they relate to universes in this context. So for me, the prototypical example of a superselection sector comes from thinking about a bar magnet. In a bar magnet, the spins at a molecular level have all aligned so as to give some overall net direction of magnetization. But there's nothing in physics that's really special about that particular choice of direction. And in particular, if we heat the magnet up, we can randomize the spins, and then when it cools back down, the spins may align in a different direction. Now, at low energies, once the spins have aligned in some particular direction, it's a little bit difficult to change them. I can't really perform a local operation that will change all the spins. Rather, in order to change the spins, I really have to heat up the magnet. I have to pump in an amount of energy that goes like the volume. So I can think of the different spin or the different choices of spin alignment then as being, well, the different choices of spin alignment are for me a prototypical example of a superselection sector. They're very hard to reach from. Different choices of overall spin alignment are difficult to move between, but in principle it's possible. These different choices are only genuinely disjoint deep in the infrared or in an infinite volume limit. And in particular, there's only one overall quantum field theory. For any one choice of spins, although it's difficult, although I have to pump in some extensive amount of energy, it is possible to randomize the spins and fall back down into a different net spin alignment. So there's really only one field theory present. Now, by contrast, in decomposition, the idea is that the different constituent universes really are disjoint at all energy scales. So there are multiple different quantum field theories present. They're sort of bumping up against one another. And what we see in the full theory is some sort of superposition of all of those constituent pieces, which leads to some fun effects. Now, there are lots of examples of this. Surprisingly, lots of examples. I didn't really appreciate this when we were first getting started. So the orbifolds are a common source of examples. The thing you need for this to happen in an orbifold is for a subgroup of the orbifold group to act trivially. And then, for example, if the trivially acting subgroup lies inside the center, then the orbifold is equal to a disjoint union of orbifolds by effectively acting cosets. So we'll come back to this later in the talk and see many examples. This is essentially going to be the subject of the second half of the talk, as I specialize to a particular application of decomposition. Now, this is not just specific to orbifolds. This also happens in gauge theories. If I have a two-dimensional, say, U1 gauge theory with non-minimal charges, that turns out to be the same thing as a sum of U1 theories with minimal charges. And to really explain that, we have to have a longer discussion about how to define charges, what non-minimal means. I'm sweeping all those details under the rug for the sake of time. Another example, a two-dimensional, let's say, G gauge theory where G might be non-abelian with center invariant matter is a sum of G mod center gauge theories with what are called discrete theta angles, which weight the different constituent universes. So for example, an SU2 theory in 2 dimensions with center invariant matter is the same thing as a sum of SO3 theories with the same matter. Another example, a more extreme example that was worked out just within the last couple of years. If I take pure Yang-Mills theories in 2 dimensions, those are the same thing as a sum of what are called invertible field theories, essentially sigma models on points, trivial field theories, indexed by the irreducible representations of G, essentially because in a pure gauge theory, the entire gauge group acts trivially. And then for another example, so far these examples have been in 2 dimensions, but there are examples in other dimensions too. If I have a 4-dimensional Yang-Mills theory with a restriction to instantons of degree divisible by k, that turns out to be the same thing as a disjoint union of ordinary 4-dimensional Yang-Mills theories with different theta angles. And there are more examples. Sorry, was there a question or?
Yeah, so what do you mean by sigma models on points? So is the target space a point or something?
Yes, it's a completely trivial theory. It has a vacuum and no other, the only state is the vacuum. So this is what Dan Fried refers to as an example of an invertible field theory. There's a very minor degree of freedom in the sense that for any 2-dimensional theory, I can add, for example, a counter term that looks like a dilaton proportional to the Ricci curvature of the world sheet. I can also add, if I want to venture outside of topological field theories, I can add a counter term that multiplies the area of the world sheet. So I don't really have just a single invertible field theory. There's sort of a family of invertible field theories indexed by these sorts of trivial counter terms. So it's a fun story. It's not really going to be important for anything else I'm going to say. If you're still curious after I finish the talk, please do ask me some more. Ask me some more then, and I can elaborate for quite a bit. So let me give a few more examples of decomposition. So another source.
Just can you say what is K in the previous example?
Oh, what is?
The last example.
Right, hang on a second. Oh, K is just some integer. So I might ask for instantons of instanton number of even instanton number. So instantons of instanton number divisible by 2. So ordinarily we don't do this for reasons involving cluster decomposition, which I will come back to later. My point is just that this is a yet another seemingly different example of how a decomposition could be. See other examples, 2-dimensional unitary topological field theories. So it's been known implicitly in the literature for a while that these are disjoint unions of essentially trivial field theories. It was pointed out, I didn't appreciate until much more recently, that these also fit into the same story. So for example, 2-dimensional abelian BF theory at level K is the same thing as a disjoint union of K invertible field theories. The G mod G model at level K is a disjoint union of invertible field theories as many as integrable representations of the Kac-Moody algebra. 2-dimensional Dijkgraaf-Witten theory is also a sum of invertibles, and that's a special case of the orbifolds that I'll be talking about for the second half of this talk. And finally, one other example. This is, I'm not going to use this word very often in this talk. It'll come up maybe 4 times, but it provides a nice perspective that unifies many of these things. This work originally started when I was trying to make sense many years ago of sigma models on certain generalizations of spaces called stacks and gerbs. And there are technical issues that arise when you try to do this. For example, a sigma model on a gerb turns out to be, well, has some issues with cluster decomposition, which are solved by the fact that it's a disjoint union of sigma models on spaces, but that's mostly beyond the scope of what I'll be talking about today. Now, I've presented some very different seeming examples. I've got topological field theories. I've got two-dimensional gauge theories with trivial group actions. I've talked about four-dimensional Yang-Mills theories with a restriction on instantons. What's the common feature? What unifies these different examples? Well, the answer is a higher form symmetry. Specifically, in D space-time dimension, a theory decomposes when it has a global D-1 form symmetry. So decomposition and higher form symmetries really go hand in hand. Now today, I'm mostly going to be interested in the case of two-dimensional theories. So we'll get a decomposition if there's a D-1 or one form symmetry present in the theory. And with that in mind, let me take a minute to explain what I mean by a one form symmetry.
Sorry, Eric. So when you say, is this it's a necessary, but is it also a sufficient condition?
To the best of my knowledge, it's both necessary and sufficient. That's right. That's right.
Okay.
But feel free to ask me. Feel free to ask me some more later after I've walked through some more of this. So today I'm mostly going to be talking about
any theory. If I find a D-1 form symmetry, then I'm guaranteed that it will decompose.
It should. It should. Unless I mean, in principle, there could be an anomaly, but so long as that D-1 form symmetry is non-anomalous, then the theory should decompose. And if you find what appears to be a counterexample, let me know. I would be very, very interested to study it.
Okay.
But I believe it's both necessary and sufficient. So what do I mean by one form? Oh,
So
sorry, was there?
Yeah, so in 4 dimensions, for instance, when you have Yang-Mills theories, if you can find a 3-form symmetry, can you find a sort of phase, can you find 2 different sectors where you have different different phases of the, well, not different phases, but different sectors of the theory, as you are saying, so that you can kind of model, say, confinement in some way?
Well, if you have a 3-form symmetry, but to get a 3-form symmetry, we'd have to have a longer discussion about when you have a 3-form symmetry. So the obvious examples in the examples that come to mind, existence of a higher form symmetry doesn't directly correlate with confinement, for example. It's an orthogonal question. In the case of the Yang-Mills theories, in the case of those 4-dimensional Yang-Mills theories I mentioned a couple of slides ago, what's happening there is that the restriction on instantons is essentially responsible for a 3-form symmetry, but those Yang-Mills theories with the restriction on instantons are equivalent to ordinary Yang-Mills theories, but with differing by choices of theta angles, so that the ordinary Yang-Mills theories all confine in the usual sense, and then the decomposition is responsible for the restriction on instantons.
Okay.
I'll keep walking through this. Give me a few more minutes to get through the introductory material, but please do keep these questions coming. This is great. This is a lot of fun. One form symmetries, right? So I may not need to walk through this for this crowd, but again, I'm going to proceed on the assumption that there may be young people present and outline what I mean when I talk about a one form symmetry. So we're all used to ordinary symmetries in which a group acts on a space or on the fields of a quantum field theory, or more precisely, we have an action of elements of the group. Well, in this talk, a one-form symmetry is going to be something like a group that exchanges the non-perturbative sectors. It provides a symmetry amongst the instantons, if you will. So one example of this will be a gauge theory or orbifold in which the matter is invariant under some subgroup of the gauge group. And there are various technicalities. If I really want to talk about a one-form symmetry, I need to assume that K is abelian. In fact, I really want K to be in the center of the gauge group. But never mind those details. Decomposition actually exists more generally. So in that special case where K is, let's say, a central subset or in the center of the gauge group, the non-perturbative sectors are invariant under the following permutation. I can take a G bundle and tensor in a K bundle in a certain sense to get another G bundle. So in effect, I can interchange G bundles. And when I do so, because K acts trivially, the original bundle will contribute to the path integral in exactly the same amount as this new bundle. So this is what I mean by a one-form symmetry. This is an action not of an element of a group, but of a bundle of groups. And depending upon where you grew up, this is denoted in one of a couple of ways. This K with a superscript 1 has been appearing in the high energy literature recently. It's also often used in the condensed matter community. BK is notation that's been used in the math community now for decades. So for various reasons, I'm going to use this notation of BK to indicate a one-form symmetry group. There also exist nonlinear realizations of these things, which are wonderful, but beyond the scope of what I can talk about today.
I have a question.
Uh-huh.
Instead of a K bundle, if you had, say, a gauge transformation for a gauge field, that would also in general leave the action invariant and the path integral invariant, right? So the K bundle
That's right.
is different from a gauge transformation in some sense.
That's right. So this is, that's right. But I think of a gauge transformation as being a local zero form symmetry, a local ordinary symmetry. Whereas you know, the actions I'm describing.
In what sense is it different? In what sense is it different exactly?
Oh, because if I'm just doing a gauge transformation, I'm not changing the bundle. I can gauge transform all I want to, but the bundle will remain the same. Whereas here, I'm actually interchanging the bundles. We'll see some more examples later. I'm going to start walking through this in successively greater levels of detail. So bear with me and we'll see this more concretely as we go. Right, so the particular field theories I'm going to be interested in can be described in one of several equivalent ways. Let me quickly walk through this and then I'll start specializing a bit more. So mostly I'm going to be talking about gauge theories or orbifolds with trivially acting subgroups, or if you will, a non-complete charge spectrum. In 2 dimensions, this is also equivalent to a theory with restriction on instantons. I can also think about this, and forgive me for this language, as a sigma model on one of these generalizations of a space called a gerb. And just very briefly, a gerb is basically a fiber bundle in which the fibers are groups of one-form symmetries. The fibers look like this, in other words. And there's also a presentation in terms of algebras of topological local operators, but I'm not going to go there. Decomposition will often relate these different pictures. So for example, we're going to see that this restriction on instantons will arise as an interference effect between the different universes appearing in the decomposition. The one-form symmetry also has a natural action, a natural description in this language, in terms of a translation symmetry. If I have a sigma model whose target space is a fiber bundle, then I expect that sigma model to have a global symmetry corresponding to translations along the fibers of the bundle. And in this case, if I have a well-defined sigma model on a gerb, a principal bundle with fibers this, then I should expect a one-form symmetry to be present, and that's part of how this works. And then finally, this business at the top about gauge theories with trivial group actions is there because these groups, these one-form symmetry groups can be described as quotients of a point. Now for ordinary spaces, if I quotient a point by a group, nothing happens. I just get the point back again. But for the pertinent notions of geometry, actually keep track of automorphisms. So this is different from a point. So BG is different from a point. And in particular, if you have something like a gauge theory with a trivially acting subgroup, a good intuition to keep in mind is that's going to be something like fibering this over an ordinary gauge theory. This is part of how all this ties together. Now, let me start filling in some details. What I want to do next is outline in a bit more detail how all of this fits together in the case of gauge theories. And then later when we get to orbifolds, I'm really going to dial down and see all the details very explicitly. So this will be at some intermediate level of detail, hopefully enough to sort of warm up what's going to happen in the orbifold case. So let's suppose we have some non-abelian gauge theory in 2 dimensions with some finite subgroup that acts trivially. And let's assume that that subgroup is in the center. So this might be an SU2 theory with adjoint matter. So the Z mod 2 center acts trivially. So this theory has a BK one-form symmetry. Now I claim it decomposes. So first off, where are the projection operators? Well, very briefly, the projection operators are going to be built from twist fields and what are called Decomposition operators, which formally will correspond to elements of the center of the group algebra. And then existence of those projectors is ultimately a consequence of something called Wedderburn's theorem in mathematics. So the different universes, the different constituent field theories are going to be in, essentially as a consequence of the math, one-to-one correspondence with irreducible representations of that trivially acting subgroup. Now, that's just sort of a high level of understanding where these projection operators are coming from. We're going to see this in much more detail later in orbifolds. Now, let me walk through partition functions. A more precise statement of decomposition is that this gauge theory up here in 2 dimensions is equivalent to a G mod K gauge theory, where the different universes come with different discrete theta angles, essentially theta angles. So for example, an SU2 gauge theory in 2 dimensions will be the same as a sum of a pair of SO3 theories. Now, perturbatively, these things are all the same. The differences are non-perturbative. And then if we think about it a bit, we might seem to come across a puzzle. The possible instantons, or well, since we're in 2 dimensions, perhaps more precisely, the possible SU2 bundles are a subset of the possible SO3 bundles. Part of what's going on here is that the choice of discrete theta angles is weighting the non-SU2 SO3 bundles differently in such a way that their contributions cancel out when I add together the partition functions. So in effect, summing over the SO3 theories projects out some of the instantons, which is part of why we can hope to get an SU2 theory in this fashion. So formally, let me write the partition function of the disjoint union in this form. So I've got a sum over the different universes, and then a path integral for each of the constituent universes. And this is the discrete theta angle contribution. It's theta times, well, a discrete invariant instead of trace of f. But if you will, think of this as being an analog of trace of f, and then you can interpret this as a theta angle term in the usual sense. Now, if I move the sum inside the path integral, that's a trivial operation, but the interpretation changes. On the left, we had the partition function of a disjoint union. On the right, summing over these different theta angle contributions gives rise to a projection operator that projects out some of the instantons. So in effect, we have an interference effect between the different constituent quantum field theories. So schematically, we're combining 2 theories to form a third. So in the SU2 example, we have a pair of SO3 theories, which we can combine together to form an SU2 theory. Now, before going on, let me just quickly check these claims for pure SU2 Yang-Mills in 2 dimensions. This is fun because we know everything about pure SU2 Yang-Mills in 2 dimensions, basically thanks to Migdal and Rusakov. So let's just look at the partition function. This works for other things as well. So the partition function of one of these theories universally looks like a sum over representations of dimensions to the power of the Euler characteristic, weighted by the exponential of the area of the world sheet and a Casimir of the representation. For the SU2 theory, we sum over all SU2 representations. For the SO3 plus theory, essentially the SO3 theory without a discrete theta angle, we sum over all the SO3 representations. For the SO3 minus theory, the partition function was computed about a decade ago by Yuji Tachikawa, and it has the same form, except one sums over the SU2 representations that are not SO3 representations. And then for trivial reasons, if I take a sum over SU2 reps that aren't SO3 reps and add in the SO3 reps, what I get is a sum over all SU2 reps. So the partition functions
may I
add.
ask something naive?
Go for it.
Yeah. So when you say instantons here, are these usual instantons classified by Chan classes, or you need other characteristic classes when you have 2 groups in action?
Yeah, so for SU2, in 2 dimensions, for SU2 and SO3, it's a bit trivial. For SO3, what I'm really using is there's a discrete characteristic class, a Zmod 2 characteristic class for the case of SO3. And I'm using that as the thing that's really driving the discrete theta angle. That's the characteristic class I'm really taking advantage of.
In higher dimensions, there'll be more characteristic or other characteristic classes that will come into place. That right guess.
That's right. So in higher dimensions, decomposition is more complicated. In higher dimensions, I would need a higher form symmetry.
Right.
What I'm taking advantage of in 2 dimensions is the fact that I only need a one-form symmetry. So indeed, in higher dimensions, there are many more characteristic classes, but to get a decomposition, I also need a higher level, higher form symmetry, which is going to involve more than just a gauge theory with a trivial group action. That will give me a one-form symmetry, which will give a decomposition in 2 dimensions. But in higher dimensions, I'd need a D-1 form symmetry, which
We'll have to change the definition of instanton a bit.
It will do that too. It will do that too.
Yeah.
But for this talk, I'm
No, I
mostly
understand. So this was
focused on
just to understand the point. Yeah, thank you.
No problem. No problem. Let's see. Yeah, I'm using instanton a little bit naively, but anyway, another feature these theories are going to have, they violate cluster decomposition. So usually this is a no-no. Weinberg taught us years ago that whenever we restrict instantons, that violates cluster decomposition, and that happens frequently in these theories. Now, the saving grace is that a disjoint union of quantum field theories also violates cluster decomposition, but in a fashion that's easy to control. If each of the constituent theories is a local field theory with a Bayes cluster decomposition, and I know how to project onto those constituents, then I sort of don't care that the disjoint union violates cluster decomposition. So the lesson I take from this is that restricting instantons can be okay, that Weinberg's argument has a loophole. Restricting instantons can be okay, so long as the resulting theory is equivalent to a disjoint union. Now, I'm just about ready to start talking about orbifolds, but before I get there, let me explain why I believe this. So I've made a bunch of what probably sound like fairly strong claims, and I want to emphasize that over the last 17 to 20 years, we've checked decomposition in a lot of examples, in a lot of different kinds of examples, in a lot of different ways. So since I grew up doing string compactifications, one of the first things we checked were what are called gauge linear sigma models that we use to build essentially string compactifications. And there one can see the structure of decomposition explicitly when one computes mirrors and when one computes quantum cohomology rings from Coulomb branches. So back 17 years ago, we did these computations for abelian GLSMs. More recently, we were able to repeat them for using more modern technology of non-abelian mirror constructions. Orbifolds, I'm going to talk about orbifolds in the second half of this talk. Open strings, there's a version of this in open strings. If I have a gauge theory with boundary, if a subgroup acts trivially on the bulk degrees of freedom, it might still act non-trivially on the boundary degrees of freedom. So the open strings, the D-branes, are going to break up according to irreducible representations of that trivially acting subgroup, the same decomposition that arises of the same decomposition that plays a role in the bulk degrees of freedom. There's also a math understanding of this. There exists, I'm told by experts on K-theory that there exists the notion of K-theory on gerbs, and it obeys exactly the same decomposition. K-theory of a gerb is the same thing as K-theory, a disjoint union of K-theories of underlying spaces. And from what I can tell, it's essentially the same reason that K-theory of a gerb looks like K-theory of a gauge theory, if you will. There's some group action on the K-theory, and the decomposition is then by irreducible representations. One can apply the technology of supersymmetric localization in supersymmetric cases. This falls right out. One can also see this in non-supersymmetric pure Yang-Mills theories. I outlined that at the level of partition functions a few minutes ago. There's also a more extreme version due to these authors that decomposes pure Yang-Mills theories all the way down to invertible field theories. It's a fun topic. I don't have time. Zohar Komargadsky and his collaborators have discussed this for adjoint QCD2. There have even been numerical checks. One group last fall looked at lattice gauge theory descriptions of this. And from thinking about the lattice gauge theory, they also saw the same thing. And then there are also versions in D-dimensional theories with D-1 form symmetries, which mostly I'm not talking about today. Now, if all I had was a game with field theory, that would be fun. But this also has a number of applications. So the original application, this will be the one of the last times I'll mention this, was to making sense of sigma models on generalizations of spaces called stacks and gerbs. Decomposition solves some of the technical issues that arise when you try to think carefully about that. There are predictions for Gromov-Witten theory here. Specifically, there exists a notion of Gromov-Witten theory for gerbs. It was checked, years ago now, that indeed the Gromov-Witten invariants of a gerb are equivalent to a disjoint union of Gromov-Witten invariants of underlying spaces. So that works. It's been applied to non-perturbative constructions of geometries and gauge linear sigma models. This is one of my favorite games, but I don't have the time to describe it. It's been applied to compute elliptic genera. For example, elliptic genera of pure gauge theories have pure supersymmetric gauge theories can be efficiently computed using these ideas. And finally, it's been applied to anomalies and orbifolds, which is basically going to be the subject of the second half of this talk. Before I get there, let me throw a few more buzzwords at you. I've outlined already, and we'll see in more detail later, how there is a notion of multiverse interference that comes out of this. When one gauge theory decomposes into a disjoint union of others, the existence of that disjoint union helps explain why the original gauge theory may have fewer instantons than you thought it might. Wilson lines, if I have a minimally charged Wilson line in the original theory, it turns into a defect between the constituent universes. So here I've outlined how this works for two-dimensional abelian BF theory at level K. The usual clock shift commutation relations between local operators and Wilson lines are equivalent to a commutation relation between projectors and Wilson lines that turns a projector on the mth universe into a projector on the m plus pth universe. And then finally, there is even a notion of Euclidean wormholes. This is basically what makes the gauge linear sigma model story I mentioned work. There's a way to apply decomposition to construct branched covers where the sheets of the cover correspond to different universes, and then the universes are joined together along some locus corresponding to the Euclidean wormhole. Now, let me catch my breath and switch gears. What I've done so
Eric, can I ask a question?
Go for it, please do.
Your observation about the Wilson lines being defects between universes, that is, I think, only true in 2 dimensions, right?
Yes, exactly,
So
exactly.
in higher dimensions, yeah, you need higher symmetry defects.
Exactly.
Okay.
That's exactly right.
Okay.
Eric, I have a quick question.
Sure.
So let's say you have a disjoint union of QFTs on the right-hand side in arbitrary dimensions. So is it true that in each of those pieces, you have QFTs whose local operator spectrum is the same, but there's some difference in the spectrum of extended objects? Is that the difference between the different pieces?
Or if you include the roughly, yes. I mean, the one way of thinking about the difference, in this context, one way of thinking about the difference, for example, is the different instanton sectors are going to be weighted slightly differently by different choices of theta angles. And that's also going to modify other things. Actually, the spectrum of local operators can be different too. So hold that question in mind. We'll see an example. We're going to see a very explicit example in orbifolds where I really dial in that hopefully will address precisely that question.
Your CPN example on that is very nice. Maybe you can later mention that.
If I don't get to it in here, please ask me afterwards, and I'll do what I can. Right. So what I want to do next is dial down to a particular application of decomposition. I'm going to discuss how decomposition works in orbifolds. Oh, sorry, I see someone has a hand up. It's difficult for me to keep track of that. If you have a question, feel free to just unmute yourself and ask. Or maybe they don't have a hand up. Well, if there's a question, feel free to unmute yourself and ask. I'm going to proceed. I'm going to go on and proceed for the moment. Right, so orbifolds. So what I want to do next is talk about decomposition in orbifolds, and in particular, apply decomposition to understand a proposal of Wang-Wen-Witten. So what did Wang-Wen-Witten do? I'm only going to touch on them intermittently until the end of the talk, because once we get through decomposition in orbifolds, we'll be able to make very short work of their idea. So their idea was as follows. Suppose I have an orbifold which has a gauge symmetry. Now, ordinarily, if I have a gauge symmetry, I just can't make sense of the gauge theory at all. I stop before I can start. But they had an idea for a fix. Their idea was to replace the original group with a larger group whose action is anomaly free. That larger group has a subgroup that acts trivially, and then the original group is the coset of the bigger group by that trivially acting subset. Now, my ears sort of perked up at this because orbifolds with trivially acting subgroups are standard examples in which decomposition arises. So here's my plan for the remaining 15 minutes or so of the talk. I'm going to really dial in and talk about decomposition in orbifolds with trivially acting subgroups. This will be a fun excuse to see lots of details. I'm then going to add a new modular invariant phase, which will be some analog of discrete torsion, but will be specific to orbifolds with a trivially acting subgroup. I'll then review in detail the anomaly resolution procedure of Wang-Wen-Witten, and then apply decomposition to that procedure. And what we're going to find is the following. If we apply the Wang-Wen-Witten procedure, we replace some anomalous G orbifold with a non-anomalous gamma orbifold with a quantum symmetry turned on, then that's going to be equivalent to copies and covers of orbifolds by non-anomalous subgroups of G, which is going to give a very simple understanding of why Wang-Wen-Witten works. All right. Now, decomposition in orbifolds. So let me begin by talking about decomposition in ordinary orbifolds without extra phases. Let's consider an orbifold X mod gamma, where a subgroup K inside gamma acts trivially. So decomposition implies that that gamma orbifold is going to be the same as a disjoint union of G orbifolds, as many as irreducible representations of K, and each with some phases, what are called discrete torsion in this context, but you can think of as basically being theta angles. So this is very closely analogous to the relation between an SU2 theory and SO3 theories that I mentioned earlier in this talk. The gamma orbifold is the analog of the SU2 theory. These are the analogs of the SO3 theories. Sorry, is there a question?
Yeah, so when you mean, what exactly do you mean by disjoint union of different theories? Are the theories in different spaces? In the sense of space times?
The space-time is the same, but the degrees of freedom are completely independent. There's a longer, and furthermore, I mean a sum and not a product. So here's an example of what I don't mean. Take a pair of free scalar fields. That's a product of theories corresponding, each of which has a single scalar field. So that's not what I mean. The states in that theory are a tensor product of the states of each of the two free scalars separately. What I really mean is a sum of theories. So here the state space really is a sum of the different state spaces. And so there'll be multiple different identity operators and so forth. I don't know if that answers the question, but maybe if I walk through some more details, it will become a bit more clear.
Okay.
Right, so first off, projectors. From what I told you at the beginning, I need to give you projectors. And here they are abstractly. We'll see in a specific example what this really means. Suffice to say, there's a standard expression for projectors built from twist fields for the trivially acting group elements. So these tals are those twist fields, and the rest of this is just the linear combination of twist fields you need in order to build a projector. In fact, this formula for projectors is essentially standard mathematics. This is a result of something called Wedderburn's theorem. So there's some standard mathematics behind this particular formula. Now, let me talk about a specific example and really.
So here, K has to be a finite group, right?
Sorry. Yes, K has to be a finite group for the orbifolds discussion, and for most of everything else, there have been some lovely new works by Sherman Jacobson and Nagoyan, Tanizaki, and Unzel, in which they've looked at cases in which the trivially acting subgroup is not a finite group, but that's beyond the scope of what I'll be talking about today. So let me dial into a particular example. Let's consider an orbifold by the 8-element dihedral group. So this group has a Z mod 2 center. Let's take that center to act trivially. In this case, the prediction of decomposition is that the D4 orbifold is the same as a disjoint union of a pair of Z2 cross Z2 orbifolds, one with discrete torsion, one without, basically different theta angles on each of these two factors. This is a very close analogy of the relation between the SU2 theory and the two SO3 theories. It's that same sort of pattern. Now, let me check this explicitly. First off, I need projectors. I gave you a general formula, but here we can actually just eyeball it. If a Z hat denotes the dimension 0 twist field associated to that trivially acting Z2, well, it squares to 1, and so we can almost immediately build projectors which have this form. It's a specialization of the formula from Wedderburn's theorem, but it's so easy in this case, you can basically write it down by inspection. So that gives us projectors. That tells us that the original theory breaks into two pieces, but it doesn't tell me what the pieces are. In order to understand what the pieces are, next let me compute partition functions. So to do that, I need to say a little bit more about the dihedral group. I'm going to describe the dihedral group as generated by the center Z and then two other elements A and B. And then all the other elements here are products of Z, A, and B. So there's an AZ, there's a BZ, there's an AB, and then there's a BA, which is just almost AB up to an element in the center. Let's take, for simplicity, the two-dimensional spacetime to be a 2 torus. Then the partition function of any orbifold on a 2 torus has this universal form shown, where those ZGHs are basically path integrals from 2 tori with branch cuts. The idea is, or if you prefer, we could think about these as path integrals over maps from squares into the target, where the two vertical sides are related by G and the two horizontal sides are related by H. And then the condition that G and H have to commute with one another corresponds to the fact we want this to close into a square. If G and H don't commute, then the image of the lower left corner isn't one point. G and H have to commute for the upper right corner to be a single point. And then we're going to see that the partition functions add. And unfortunately, my laptop and my pad seems to have gotten out of sync. Bear with me for just a second while I restart the share to get that working again. Come on. Right. Okay. So let's compute the partition function. The D4 partition function will look like a sum over commuting pairs in D4 of these ZGHs. Now, since the center of D4 acts trivially, there is a symmetry amongst the ZGHs. The ZGHs only really know about boundary conditions, and Z doesn't change boundary conditions. So this sector is the same as this sector, as this sector, as this sector. So this is a symmetry amongst these sectors, and moreover, in an orbifold, these are the non-perturbative sectors. And this is an orbifold is a finite gauge theory. A finite gauge theory has no perturbative degrees of freedom, only non-perturbative degrees of freedom. And so these are those degrees of freedom. Now I can move between these by tensoring in Z2 bundles. Each of these sectors is essentially, up to automorphisms, a D4 bundle. And I can get between any two of these D4 bundles by tensoring in a Z2 bundle, as I've illustrated here. So not only do I have a symmetry amongst the non-perturbative sectors, and I can permute the different symmetric sectors by tensoring in Z2 bundles. So this is that BZ2 symmetry, that Oneform symmetry I mentioned earlier. Now, each D4 sector that appears is basically the same as a Z2 cross Z2 sector, just with multiplicity, a factor 4, because I can multiply in the Z's, but there's a catch. Not all Z2 cross Z2 sectors can appear. For example, this A bar B bar sector, this would be a fine contribution to a Z2 cross Z2 orbifold, but I cannot lift A bar and B bar to a commuting pair inside D4. So A bar lifts to A and AZ, B bar lifts to B and BZ, but if you look up here in the multiplication table, AB and BA do not commute with one another. And then similarly for these others. So this means there's a restriction on the possible non-perturbative sectors. We only get some of the non-perturbative sectors of the Z2 cross Z2 orbifold, not all of them. That's another common feature of these theories. So let me pause to put this in perspective for just a minute. If we put what we have together so far, we see that the D4 partition function is the same as, well, it's similar to a Z2 cross Z2 orbifold partition function up to factors, except we have to subtract out what turns out to be a modular orbit of some of the twisted sectors. So in particular, this is a different physical theory. Nowadays, this might not be so surprising. I could phrase this by saying that the D4 orbifold has a one-form symmetry. The Z2 cross Z2 orbifold does not have a one-form symmetry. Since they have different symmetries, they must be different theories. But I think for the first decade I was giving talks on this, this was a point that people kept getting hung up on. How can physics know about gauging something that's acting trivially? So, after 10 years of giving talks, or after having answered that question many times, I've thought it important to emphasize that point. Now we can clean this up some more. Given any one orbifold, I can multiply in some modular invariant phases to get a consistent partition function for a different theory, which has this form. There's a universal choice of such phases called discrete torsion. And in fact, in a Z2 cross Z2 orbifold, there is, well, one non-trivial choice of discrete torsion, which acts on exactly these contributions by a sign. These are the same sectors that I omitted to build the Z2 cross Z2 orbifold. So what this means is I can take this T2 orbifold partition function and write it equivalently as a sum of a pair of Z2 cross Z2 orbifold partition functions, one with discrete torsion, one without. These sectors that were omitted from the Z2 cross Z2 orbifold, their contributions cancel out when I add together the two orbifold partition functions. So this is that interference effect I was mentioning earlier. And then, of course, this matches the prediction of decomposition in this case. Now, so far, I've just computed two torus partition functions. You can do the same at higher genus. There's just more combinatorics, but if you want to see it done, there's where you can find it. Let me extract one other bit of physics before going on. Let me talk about the massless states. I can compute the massless spectrum in the case that the covering space is a 6 torus. I've written it in the form of a Hodge diamond. And this looks a little problematic on its face because of the 2s in the corner. So those 2s in the corner signal a violation of cluster decomposition. They're there because we have multiple vacua, multiple dimension 0 states. It's the same axiom that's violated by restricting instantons. Now, ordinarily, if a student came to me with this kind of result, I'd pat them on their head and send them back and say, okay, try again, you made a mistake. But in this case, decomposition saves the day. It turns out that this is the same thing as the sum of the massless spectra of a pair of Z2 cross Z2 orbifolds with and without discrete torsion. So in particular, in this example, we can see that the spectrum of local operators in the two constituent universes are actually different from one another. That said, the local operators in an orbifold include twisted sector states. And to what extent I want to think about a twisted sector as a local operator, maybe as a discussion for another time, but at least in principle, we can see a very significant difference between the operators I would do computations with in the constituent universes, but they correctly add up to give the massless spectrum of the D4 orbifold. Now, I've spent a lot of time talking about cases in which the trivial acting subgroup was in the center. There's another story that happened.
Just a small question. So,
sure.
So in the previous example, these two caladios, are they like mirror of each other? Or?
In this particular example, they are. It's not a general feature of decomposition, which is why I didn't say anything about it. In general, the constituent universes of decomposition don't have to be mirrored to one another. In this particular example is a little bit too cute. The constituent universes actually are mirrored to one another. Right, so there's another story. If the trivially acting subgroup is not in the center, you get different universes, but I'm beginning to run out of time. Let me get back to Wang.
About the time, I think you started a bit late. So there are many questions, so feel free if you need more time, you can take a bit more.
Okay, but I'll still try to end up pretty quickly.
Yeah,
Other people have schedules and whatnot. Right, let me get back to Wang-Wen-Witten. So what did Wang-Wen-Witten do? So their idea was they had an idea for a fix for gauge anomalies. They started with an anomalous orbifold, anomalous in the sense of having a gauge anomaly, which ordinarily means I'd have to throw it out. I couldn't do anything with it. Their idea was to replace the original orbifold group with a bigger finite group and add some phases. Now, if all I did was replace G by a larger finite group, that wouldn't help because that gamma orbifold would just decompose into copies and covers of the G orbifold. So we have to add some phases, which is an important part of their story. So the phases we add, the phases that have to be added are what we decided to call quantum symmetries because they generalize the old notion of quantum symmetries in the orbifolds literature. Basically, they give away for the subgroup that acts trivially on the covering space. We allow it to act on the twisted sector states by phases. So in terms of the quantities I've been drawing, that basically means we add a possible phase difference between that sector and that sector. Now, there's a story about why these are modular invariant. Suffice to say, well, let me move on. The quantum symmetries live in this particular group cohomology group, which is related to a group cohomology group containing discrete torsion, and another one that encodes the anomalies in an orbifold. In special cases, these quantum symmetries will correspond to old-fashioned quantum symmetries. That will be the case when the quantum symmetry is in the image of that map beta. But for the purposes of resolving anomalies, we're going to want a quantum symmetry that has a non-trivial image under this map D2. Now, if you turn on such a phase, if you turn on a quantum symmetry, one should work out what decomposition does, and here's the answer. The field theory of a gamma orbifold with a quantum symmetry is the same as copies of orbifolds by a subgroup of G, where the subgroup of G is determined by the quantum symmetry. I can rewrite this group cohomology group basically as homomorphisms from G into irreps of K, and then if I do so, I can talk about the kernel of B, where B is now a homomorphism from G into K hat, and that defines some subgroup of G, which is what's appearing here. And there's a long story about why this has to be true. It's essentially uniquely determined by consistency with decomposition of orbifolds with discrete torsion, which I haven't really had a chance to talk about. But to my mind, more importantly, when you check it in examples, it works. So let me move on. I think there's one other piece I need. So I said that Wang-Wen-Witten takes an ordinary anomalous orbifold, they make the orbifold group bigger, they turn on a quantum symmetry. How does this relate to the anomaly? Here's the answer. They turn on a quantum symmetry that maps to the anomaly under this map I've labeled D2. So they turn on not just a random quantum symmetry, but a particular quantum symmetry that maps to the anomaly. Now, with that in mind, we can outline the algorithm. So Wang-Wen-Witten basically has two steps. Step one, they make G bigger. Step two, well, if all I did was make G bigger, that wouldn't accomplish anything. But if I now add a quantum symmetry, I'm in business. I make G bigger, I add a quantum symmetry, that's chosen to map to the anomaly that lies in that group cohomology group. And then those two things together resolve the anomaly. Now to see why, we can apply decomposition. So if I apply Wang-Witten to an anomalous G orbifold to turn it into a non-anomalous gamma orbifold with a quantum symmetry, then the field theory of that gamma orbifold is a sum of field theories of orbifolds by the kernel of B. However, because B maps to the anomaly, if we restrict the anomaly to the subgroup given by the kernel of B, we automatically get 0. So this subgroup defined by the kernel of the quantum symmetry is automatically anomaly free. Now, in my remaining maybe 60 seconds, let me outline how this works in examples. So here I've outlined a particular example. I take I start with an anomalous orbifold where the orbifold group is a Z2 cross C2. The anomaly for a Z2 cross C2 lands in, degree 3 group cohomology, which turns out to be a Z2 cubed. Those 3 Z2s basically correspond to the 3 Z2 subgroups of Z2 cross Z2. So if I think of Z2 cross Z2 as generated by A and B, then there's a subgroup generated by A, a subgroup generated by B, and a subgroup generated by the product AB. Now to apply Wang-Wen-Witten, I make two choices. First, I extend the original orbifold group to something bigger. Let's extend it to the dihedral group. Second, I pick a quantum symmetry. In this table, I've outlined all possible quantum symmetries. The first line is what happens if I don't turn on any quantum symmetry at all. In this case, we just get copies of the original G orbifold back, which is not particularly useful. The last two lines are more interesting. Here, for these two quantum symmetries, the image is non-trivial, so I could resolve an anomaly that lies in this subgroup. And then if I turn on that quantum symmetry, then this D4 orbifold with that quantum symmetry is equivalent to basically one of these four orbifolds, none of which involves an orbifold by that subgroup. And so if the anomaly lies in here, these four are all automatically anomaly free. And then there's nothing unique about any of the choices I've just made, but this continues to work for all choices. For example, if instead of extending Z2 cross Z2 to the dihedral group, if I extend it to the 8-element group of unit quaternions, I can do that too. Here's a table listing all the possible choices of quantum symmetry. The details vary, but the result's the same. For any quantum symmetry whose image could encode an anomaly, we get a result for the orbifold, the resolved orbifold, that does not intersect the anomaly. So Wang-Wen-Witten works. Here's another example. Instead of extending, we extend Z2 cross Z2 to a Z2 cross Z4. Again, the details are different, but the pattern is the same. Wang-Wen-Witten's works. Instead of picking a minimal resolution, I could extend by something non-minimal. I could extend by a product of two Z2s. The only real difference is that instead of getting one orbifold over here, we get copies of an orbifold, multiple orbifolds, a sum of orbifolds coming out. Okay, I think I'm a couple of minutes over time. Thank you for bearing with me. Let me just quickly summarize. If you remember only one single thing from this talk, then it should be the following, that decomposition is a statement that what you thought was one quantum field theory is actually several different quantum field theories. They're sort of sitting on top of one another. So if you remember only two things from this talk, let the second thing be that decomposition can happen when you have an n+1 dimensional theory with an n-form symmetry. So I focused on examples in 2 dimensions, but examples do exist in other dimensions as well. And then finally, if you remember only 3 things from this talk, let the third thing be that decomposition can be applied to understand, for example, the anomaly resolution procedure of Wang-Wen-Witten. They start with some anomalous orbifold, replace it with some larger orbifold with quantum symmetries, but decomposition implies that the result of their procedure is equivalent to a disjoint union of orbifolds by non-anomalous subgroups, which is explicitly non-anomalous. That, to my mind, is a very simple, clean understanding of why Wang-Wen-Witten works. The orbifolds they're building are equivalent to orbifolds in which there is explicitly no anomaly at all. So it's no wonder that the anomaly is resolved. And with that, I'm going to close and ask if anyone has any questions.
I have a question.
Thanks a lot, Eric, for the great talk. Yes, so any questions?
Yeah, so I have a question. Like when you say that different quantum field theories can coexist at the same time, what would that imply, for instance, for the vacua? Because you can't have different vacua coexisting at the same time, right?
Well, you wouldn't in a theory that obeys cluster decomposition, but that's sort of, these theories break cluster decomposition. They're also completely decoupled from one another. So, so long as the theories are decoupled, there's no particular obstruction to having theories coinciding. If I have if I have 2 different quantum field theories that take place on the same space-time but don't talk to one another, then there's no no-go theorem that makes it impossible to have a that says, okay, one has a Kac-Moody symmetry, therefore the other, therefore this one can't have multiple vacua. That's what makes this work. I mean, if you had if there weren't a decomposition, if you had multiple dimension 0 operators, but the different sectors were all talking to one another, that would be a problem. But what makes this work here is that although you have multiple vacua, multiple dimension zero operators, the different sectors can be disentangled. They're all orthogonal to one another. They don't have any interactions at all. So because they don't have any interactions, there's no issue. That's the way I think about it.
So Eric, I was wondering, like, how do you think intuitively about this turning on this quantum symmetry? Is it like turning on the background gauge field of a sort, or?
The way I think about it is really just like discrete torsion. That's how I think about it in the back of my mind. If I turn on discrete torsion is some discrete choice. I can turn it on. It's sort of analogous to adding a theta angle. And then if in an orbifold I happen to turn on discrete torsion, it does have some significant effects. It changes the massless spectrum and hence interactions and all that. I think of these quantum symmetries in exactly the same fashion. It's some discrete choice I can make. If I make that choice, then I get some new spectrum. I've changed the theory in some fashion. And because it's a discrete choice, there's no way I can sort of dial it on and off. There's no reason it has to be continuously connected in any sense to the theory without a quantum symmetry. It's a discrete choice, very much like discrete torsion. Or phrased another way, it's another way to build a modular invariant phase. Anyway, that's my answer. I think of it exactly as it's a discrete choice that's very similar to discrete torsion in my mind.
I have another question. When you say that the two theories are completely decoupled from another, in that case, how can they interfere in some cases, as you're saying?
Because you have operators with a non-trivial projection into each of them. That's a fine question. If you only look at operators that sit exclusively in one universe, they can't know about the others. But the reason you can see this is because one reason is because you're computing partition functions. You sort of have a godlike perspective. You're sitting outside of all of this. And so you can see that, sort of seeing them layered on top of one another. Another answer is that one can build operators that have a non-trivial projection into each of those universes. The results of that projection are completely orthogonal to one another. But for example, in an orbifold, if I take just an invariant untwisted sector state in the original theory, that projects to something in each of the constituent theories. The results of that projection are orthogonal to one another, but I can, there's some big messy glob in the original theory that has pieces in each of those. So it's in that sense that one can see something like an interference effect.
Excuse me, sir. I have a doubt. Actually, I want to ask that what are the mathematical theories which are required to study the continuum mechanics? I'm off from quantum mechanics. I'm asking for continuum mechanics.
So what could you ask the question again? Your voice is sort of breaking up. It's difficult for me to understand. So you're asking about the mathematical theories needed to understand not quantum mechanics.
Continuum mechanics.
Oh, that's a fine question, and I actually don't know I don't have a good answer for you. So in this talk, quaternions popped up a couple of times, but just as an example of a group. Specifically, the group of the 8-element group of unit quaternions, plus or minus 1, plus minus I, plus minus j, plus minus k. However, that's the only extent to which I've used quaternions in this particular talk, just as an example of a finite group, just in the sense that the unit quaternions form an example of a finite group. I'm vaguely aware that people have thought about reformulating quantum mechanics using quaternions, which it sounds like what you're driving at, but I don't have anything useful to say about it.
But I can reform the question to a specific one, that is the mathematical theory, especially used for theories of plasticity and elasticity.
Oh, continuum mechanics. Sorry, I completely misunderstood your question. So if you're asking about the mathematics required to understand just continuum mechanical theories.
Yes.
So, okay, sorry, I completely misunderstood what you were driving at. I apologize. For that, I would think, yeah, I guess the way I would tend to think of it is in terms of tensors. That may not be the most productive approach for depending upon where you want to go with it. But I think the idea in the back of my mind would be, the first answer that comes to the back of my mind is to apply some version of differential geometry. Think about the stress tensor of a continuous medium. Yeah, so I think if I understand the question you're asking, and I'm not certain I do, I think just tensors might be a good mathematical tool for getting at just ordinary classical continuum mechanics.
Yeah,
maybe I'm still not getting it.
Tensor in the basic manner. I want to know about in actually tensor itself a low level thing for continuum mechanics. I think so. There are more than tensors, I feel.
Fair enough. I mean, there's depending upon where you want to go with it, there's I mean, people have certainly written entire books on such things. There's fluid mechanics, which is a closely related field. There's the Navier-Stokes equations, and people have certainly written whole books on solving the Navier-Stokes equations and various limits and approximations and so forth. I'm not certain if that helps either, but it's something else.
I think Kushik has a question. He raised his hand.
Okay.
Yeah. So is it correct to think about this x by g that you have done as a GIT quotient, where you are writing the x by g as a join, which you have also used earlier, like in the Gulkin's construction of join of two spaces, and you are considering quantum field theories on that, and it looks like something like that is going on. Is that right?
It's true. I've written papers on joins, but actually the joins appearing there are have a different interpretation.
I know. I'm simply asking because it looks like this H2 that you get at the discrete torsion part comes from the interval of the join here. Actually, most probably I can manufacture it that way.
That's a fine question.
Yeah, if I wanted to generalize to higher group cohomologies, etc., this might change. But in these particular examples, in the 2 dimensions, that seems to be the picture. Am I wrong?
So you've touched on several things. Let me see if I can just quickly get through a few of them. So first, let me go back to GIT quotients. Certainly, I can describe many of these supersymmetric gauge theories as GIT quotients. In the case the group action is trivial, that I'm really working with what I think of as a stacky GIT quotient, and depending upon what generation you're in, that may be exotic or not. When I grew up, the first time I learned about GIT quotients, it was just about as taking proj of the invariant subring of some coordinate ring. And then if you have a trivially acting subgroup, proj doesn't care about any of that. But there exists a stacky version of that which keeps track of automorphisms, and that's part of what's going on here. In terms of the group cohomology, hang on a second. There is something. Sorry, let me see if I can just quickly go back to it. So in terms of this sequence here, 2 dimensions is popping up because, actually, let me say a bit more. This sequence I've written is a 2-term extension worked out by Hochschild of the usual inflation restriction sequence. Inflation restriction usually ends right here. I think the image of the last step of inflation restriction is really this kernel. So you can add these 2 steps. What we're taking advantage of is specific to 2 dimensions in the sense that it's in 2 dimensions that the anomaly lands in degree 3 group cohomology. In higher dimensions, the anomaly actually lands in higher degree group cohomologies. For example, in a 3-dimensional orb. Okay, it sounds like you're aware of this, so forgive me if I just quickly.
No, it's just fine. It's fine. Exactly. Right. So that's where you will get discrete higher form kind of stuff.
In principle, that said, I've tried looking at, in fact, with Daniel Robbins and Thomas Vandermeulen, and the three of us have tried looking at the analog of this in 3 dimensions. We're, as an ordinary orbifold, we're very confused about how the analog, Wang-Wen-Witten story in 3 dimensions. I mean, there's some, I don't have it at my fingertips, but we tried sketching out an analog of a quantum symmetry. There's sort of a couple of different things you could try, maybe a degree 2 cohomology valued in degree 1, or things like that. Looked at, or rather, how it instead of a D2, we'd work with a D3. This, we take a variation of this whose image lands in the the relevant E2, so it makes sense to talk about, or the relevant E3, so it makes sense to talk about that particular differential. The relevant differential we need has to land in degree 4 group cohomology for the 3-dimensional case. The upshot is we've never quite been able to make Wang-Wen-Witten work for, we haven't been able to find an analog of this story for understanding Wang-Wen-Witten in 3 dimensions. There's a different story we've tried playing with in 3 dimensions, which is instead of taking ordinary group orbifolds, we've tried extending by G to a 2 group. So we are working on a paper now in which we consider 3-dimensional orbifolds, not by ordinary groups, but by 2 group extensions of G. There we're still setting up basics, but in that case, one could imagine that there might be a version of this story, but I have even less to say about these details. We're still making sense of orbifolds by 2 groups in 3 dimensions.
So when
I'm
you
sorry, I don't know if I answered your...
Yeah, 2 groups, etc. It's not only an action, it's not only a GIT, right? It has to have more.
That's right. That's right.
Yeah.
So in a 2-group orbifold, yeah. That's right. You're not just really. I think I'd quit out of Keynote and try using something else. Basically, when I think of a 2-group extension, I'm basically thinking of a short exact sequence like this, but where K is replaced by BK, and then this you could understand in various ways as a cross module, as what have you. There's a similar, there seems to be a similar decomposition story for a 3-dimensional orbifold with a trivially acting BK. Sort of from a physics perspective, if I gauge a trivially acting 1-form symmetry, I should get a global 2-form symmetry, which in 3 dimensions would give rise to a decomposition. And then mathematically, in terms of how the mechanics of this work, in fact, what I really, there's a lovely story. It would take me about 10 minutes to explain, and other people may have questions they want to ask first. But basically, there's a way of describing decomposition in the case of central extensions, in which I think of the gamma bundles as being a restricted kind of G bundles, and we believe we can play the same game with 2-group bundles. If I have a 2-group given as an extension of G by a BK, essentially the possible 2-group bundles I can build on 3 manifolds look like G manifolds with a restriction which is naturally implemented by an analogous decomposition. So there seems to be a story at that level, and then how to add quantum symmetries, how to map to anomalies if I have a 2-group extension rather than an ordinary group extension. This part of that story I don't understand at all. But would be happy to discuss if you have some thoughts along those lines.
Yeah, let's see if someone else has a question. Otherwise, I can ask a little bit more.
That's fine. I'm happy to stick around for a while and chat at length. But yeah, as you said, let's see if other people have questions.
So I have a question.
Okay.
If I think of quantum field theories in, say, the Atiyah-Siegel picture, as some rule which assigns
right, as a functor.
Then what does decomposition mean? That it takes a manifold to the direct sum of 2 Hilbert spaces? And
it's yes, and the right way to set that up in functors I don't quite know. I do know that there is old work, exactly the same crowd that's thought about the Atiyah-Singer-like presentation of topological field theories have also pointed out, it's sort of been known for years now, that the local operator algebra is semi-simple. So it admits idempotence. so you can project onto individual pieces. I don't know of any paper in which they've taken that and turned it around and turned it into a statement about functors. I don't know, off the top of my head, I don't know the right way to think about, if I have, suppose I have two topological field theories, each of which I describe as a functor. So each of those separately is going to be some sort of modular tensor category, but then I want to do something like take a sum of two modular tensor categories. And honestly, I feel certain there's a right way to do this. I don't happen to know the right way to do that myself, but I think that's the question you're asking. Basically, I want to do something like take a sum of the functors, and I don't actually know how to do that myself, but I'm sure that I have every confidence it's known to experts. I'll put it like that. Does that answer the question?
Yeah, yeah. In fact, I was going to, the thing that you said at the end, I mean, I was going to ask if I could take something like the B model with some target space.
So what happens there is a bit more fun. Way back when, let me not try to page through all my slides, but way back when I talked about decomposition and topological field theories, I used the word unitary. So I talked about two-dimensional unitary topological field theories decomposing precisely because of the A and B models. So the issue there is that if I have the let me talk about the A model on a projector space. If I look at the quantum cohomology ring, that's just, at least for a non-zero Q, that decomposes. Basically, the ring is semi-simple unless I'm missing something. It looks like if I take spec of that ring, I get a bunch of points, as many as the 1 plus the dimension of the projective space. So that's an example in this context of that semi-simplicity in action. On the other hand, the A and B models, they may decompose as their topological subsectors may decompose, but I don't expect the entire quantum field theory in which those topological field theories are embedded to decompose. So if I took the A model whose target were a gerb, that I would expect to decompose. The A model whose target is just a single projective space, well, the topological subsector, that quantum cohomology ring, at least when Q is non-zero, that decomposes, but the entire quantum field theory in which that topological subsector is embedded, that does not decompose. So that's, anyway, way back, much earlier in my slides, I mentioned something about two-dimensional unitary topological field theories decomposing. This is the question you're asking gets into exactly that issue. I think of the A and B models as arising from non-unitary physical theories, and then the topological subsectors, at least for non-zero Q, decomposes, but just the topological subsector, not the entire quantum field theory in which that's embedded. By contrast with the unitary theories, Dijkgraaf-Witten theory, the G-mod G model, BF theory, those things, the topological subsector is the whole theory. There is no quantum field theory outside of the topological subsector. So decomposition of the topological subsector is decomposition of the entire quantum field theory.
Thanks.
No problem. Other questions?
Just maybe a vague question.
Go for it.
So you mentioned that one motivation for this was to do like sigma model and stacks.
Mm-hmm.
Like, can you just explain this a little bit? Just the motivation, why would you want
Sure.
to do this and how it helps?
Well, I guess the original motivation was sort of like why the mountaineers wanted to climb Everest, because it was there. For me as someone working in string compactifications, back when I got started, one of the issues that motivated people was what's the set of possible collabials? What things can we compactify strings on? Just how many possibilities are there? And stacks they're a lot like spaces. They have, I can put metrics on them, I can put spinners on them, they can have bundles, they can have all of that structure. So given that structure, can a string propagate on a stack? So that was certainly one good question. Can we, what other conformal field theories exist? Can we build new conformal field theories, or maybe give a geometric understanding to some abstract conformal field theories used by thinking of them as sigma models whose target spaces are stacks? So for me, I think that was the one of the original driving motivations. What other conformal field theories are there? Can we construct new conformal field theories by looking at sigma models on stacks and gerbs? And there are various technical puzzles that pop up when you get into it. The 0th order puzzle is, what does an action look like? I know what an action is for a sigma model on a space, and granted, a stack it's got metrics, it's got spinners, but what does it actually mean to write down an action? And the answer goes like this. For a given stack, first I have to find call it a physically admissible presentation. Not all possible. I don't know how to assign physics to every possible presentation of a stack, but every Deligne-Mumford stack I'm going to care about admits a presentation which I can describe in physics. And what those presentations generally are gauge theories. So talking about stacks is a fancy way to talk about gauge theories. That's what it comes down to. Then there are secondary issues. A given stack can have multiple different presentations. Each of those presentations may be a gauge theory, but they may be very different looking gauge theories. For example, some of them may be orbifolds, some of them may be U1 gauge theories. In a supersymmetric context, a U1 gauge theory comes with D terms and whatnot, so it's not sitting at a fixed point of RG flow. An orbifold, if I'm really talking about presenting as an orbifold of a Calabi-Yau, that is at a fixed point of RG flow. So I've got one stack, multiple presentations, but already the physics of these presentations is a bit different. Some are at fixed points of RG flow, some aren't. So the next order, a better statement is that stacks seem to correspond to universality classes of RG flow. So I pick a stack, I pick a presentation that I can turn into physics, and then I basically go to a fixed point of RG flow, or work with some universality class of RG flow. And then that fixed point or that universality class is the thing I can meaningfully associate to the stack. And then then after you sort of get past that setup, then you get to the fun questions. Like in the case of gerbs, you have multiple dimension 0 operators. The theory seems to violate cluster decomposition. Why does it make sense? What's going on? There were a bunch of headaches of that sort. There were also questions about moduli. If I take, say, an orbifold C2 mod Z2, an orbifold is a special kind of stack. But there's a funny thing about the moduli. Physically, in that orbifold C2 mod Z2, there's a blow-up modulus in which I just blow up that orbifold and turn it into the space that's a resolution of C2 mod Z2. As a stack, the stack doesn't have any such modulus. Ordinarily, if I have sigma models on spaces, one of the basic consistency conditions I can apply is that the sigma model should have as many marginal operators as the target space has moduli compatible with Ricci flatness and so forth. But let's say moduli of a Ricci flat metric. And there was another puzzle, and that stacks seem to violate this prescription. There just don't seem to be as many moduli connecting. And then there were other puzzles. Back at the time this was new, I guess there were various other pictures of orbifolds floating around in the physics community. One of them that dated back to the time of the string duality revolution was the observation that another property of that orbifold C2 mod Z2 is that it's a limit of, if I'm really very careful about where it sits in the moduli space of conformal field theories, what we find is that it's at the limit of a non-trivial B field. It's at the limit of, it's a blowdown limit of the resolution C2 mod Z2, but with a non-trivial B field on the exceptional divisor. So, Witten for a while was very excited about the idea that orbifolds should be the same thing as spaces, but with B fields shrunk into points. And I always used to just sort of hold my head in pain. What does it mean to have a B field shrunk to a point? I don't really understand what that is. And what, if anything, does that have to do with twisted sectors and the other stuff appearing in orbifolds? And then a few years after that, that was replaced by another somewhat unsatisfactory story. It was popular at another point in time to look at D-brane probes of these things. A D-brane probe of an orbifold will always see a resolution. So if I take a D-brane probe computation in C2 mod Z2, I always get a resolution of C2 mod Z2. If I apply a D-brane probe to a space with a terminal singularity, I will get, well, a space again that even in those cases, and there were various claims that D-brane probes should see shorter distance physics than ordinary closed strings, but that argument only really makes sense to me if you're working on an honest to goodness space, so that I can really talk about short distance things. If I have something that's not quite a space, what's the D-brane probe argument doing? It's always, the D-brane probe argument will always generate a space, even from things that aren't spaces. Are they? And anyway, there were many fun and exciting puzzles way back when, but I think I probably wanted a bit far. You were asking how the setup is. I think the short answer is, for a stack, I pick a physically implementable realization, and then to that realization, typically I'm going to get a gauge theory. And then really what we care about universality classes of those gauge theories. That's how I really think about a sigma model on a stack. And then there can be other presentations. There can be things like groupoid presentations for which I have no idea how to assign any corresponding physics. On the other hand, as a stack, I can rewrite that groupoid in another fashion, which I do know how to turn into physics. So I don't know how to associate physics to every presentation, but I do know how to assign physics to, but every stack has at least one presentation for which I do know how to assign physics. And that's the game we play.
Yeah. Okay, thank you for the very comprehensive answer.
Sorry, I think it went on for probably much longer than you had in mind.
It was a great review of the history. And
Fair enough.
I've
been thinking about these things for too long.
Yeah, can I sort of continue with this question? On the
Please do. Please do.
Just before that, I just have a small question.
Okay.
Are algebraic varieties subsets of stacks, or stacks are subsets of algebraic varieties?
Varieties are subsets of stacks. So spaces in the non-technical sense are special cases of stacks. So stacks really do generalize spaces in that sense. On the other hand, I mean, the things they generalize to, are somewhat less interesting. When a given presentation of a stack will be turned into a gauge theory, it might be a trivial gauge theory in which the gauge group is nothing at all. So that's how you get a space as a special case. It could be a non-trivial gauge theory, but then we already know gauge theories. For a while, I had high hopes that we might get something new from gerbe theories. These appear to be theories with exotic properties people hadn't looked at before. But then decomposition solved problems with those gerbe theories and also told me gerbe theories were boring in the sense they were all completely equivalent to just disjoint unions of things we already knew. There's one corner that hasn't been quite adequately explored yet to my mind. If I have maybe if I look at a heterotic compactification in which the right movers land on a gerbe and the left movers land on some bundle, which is not a pullback from the underlying space. There's a potential for something new there. In the case of orbifolds, these ought to correspond to just some asymmetric orbifolds, and there's a huge literature on asymmetric orbifolds, and I suspect that the examples you can build in that fashion as toroidal orbifolds are already in the literature somewhere. I've tried to build examples that aren't toroidal orbifolds, but when I've tried this, I've run into technical problems. For example, I can write down gauge linear sigma models describing 0-2 supersymmetric theories of exactly that form, where the right movers talk to some gerbe and the left movers talk to a bundle that's a bundle on the gerbe that's not a pullback of a bundle on the underlying space. But I do not understand the properties of those heterotic string theories. I'm not convinced I'm understanding them correctly. I wrote up some attempt to understand that. I have some paper from a number of years ago with Bert Overt, Laura Anderson, and a couple of others. And it's the only paper I've ever written with both Bert Overt and Laura Anderson. So that uniquely characterizes it on spires. We try to grapple with that issue. There are some special cases in which we know what's going on, but in general terms, The interesting cases, I just don't understand.
So are the stacks you're talking about, are they global quotient stacks, or are you allowing?
Yeah, I mean, that's basically what the physically realizable ones turn out to be global quotient stacks. And I see the other end up, but we'll get back there. But yeah, the physically representable ones are precisely global quotient stacks. There may be some others that can be presented, but those are the ones that come to mind. And then things like a groupoid presentation, a local orbifold presentation. The way I would actually implement those in physics is to convert them to a global quotient stack presentation, and then implement the global quotient stack as some sort of gauge theory, and go from there.
And have you thought about higher stacks, like if quotients, like point model group, for example?
Only very recently, and actually, I think this might get into Kushik's question that I was planning to get back to. So something very recently I've been doing has been looking at, I've been trying to make sense of three-dimensional orbifolds in which I orbifold by a 2 group, which is an extension of G by a BK. And in principle, that orbifold, that's a 2 stack. And it's sort of relevant here because that 2 stack in 3 dimensions ought to decompose. And one of the things I'm trying to straighten out now is the details of how that works. But to the extent I've thought about higher stacks, it's only very recently. And until honestly, until I can straighten out the basic case of an orbifold by a finite 2 group, which is an extension of a finite group by B of a finite group, that's sort of the most basic example I can think of. And until that's straightened out, so I've started thinking about it a little bit, but I don't have anything. I don't have a lot to say right now.
But this is string theory and stacks, but actually, wouldn't it be easy to think of like particle theory and stack? Or maybe.
So it sounds like you're asking a different question, which is, so I've been talking about stacks as target spaces. It sounds like you might be asking about stacks as space-times, as doing a quantum field theory on a stack itself.
Yeah, but it could be the target space of the one line, yeah. So it's
yeah, I think maybe I don't understand it. If you could repeat the question.
No, so actually, I have a very general, vague question. Maybe I can ask you. So it's just, I find it fascinating to try to generalize quantum field theory in this way. So I was just wondering, like, what, for example, I mean, can you, are there like well understood examples where you have something that is like a generalization of space-time in some sense? For example, it could be like a particle on a stack, or it could be
right. So as a target space, the answer is yes, and there are other generalizations too. So something else that pops up, and sorry, Kushik, I see you've got your hand raised. If your schedule forces you to get out of here before too much longer, let me know. We can either bump up your question or maybe Zoom sometime later. Either
maybe you should go to this question first there.
Okay. So sorry, you said it's a work in progress, so pardon me if it's improper. So when you said that, so you already mentioned about how in olden days we talked about quotient orbifolding on using the monomial ideals, etc.
Yeah.
Now, and one knew how to use do the quotienting with discrete groups on the monomial ideals. Now, when you go to the 2 groups, for example, if I thought of very explicitly about with a Calabi-Yau manifold, say a quintic or something, which I can write it as an ideal in as a monomial ideal. So you of course have this quotients on the coordinate ring. But then what extra do you have on the, so do you somehow act also the coherent shifts or some such thing by something, or how exactly do you?
That's right. In fact, let me quit out of Keynote and open up a page in GoodNotes, because that would make it easier for me to write something relevant. Hang on a second while I get this set up.
Sorry for keeping you too late.
No, it's good. I'm happy to stick around for a while. That's not a problem at all. Hang on. Let's see. Yeah, so come on. Okay, so here's an example that I think gets to your question. Let me first describe a Derby version of the quintic, and this may be completely obvious, and I apologize if it is, but it seems like it's the right place to start this discussion. So, as you know, the ordinary quintic is we think of as a degree 5 hypersurface inside CP4. There is a Derby version. In fact, there are several Derby versions, but let me just talk about the one that looks like a degree, a hypersurface in a weighted projective space. And let's take the weighted projective space to all have weights K, and then look at a degree 5 K hypersurface inside there. So mathematically, this is a hypersurface in a Z mod K gerb. So this part is a ZK gerb on the projective space P4. So we could talk about a degree, just a hypersurface inside there. What that's going to mean at the level of things like monomial ideals is a degree 5K hypersurface in a weighted projective space where all the homogeneous coordinates have weights K is going to be basically the same thing as, to a certain extent, it looks almost exactly like the ordinary quintic.
That
so
will be a
an
scheme
example.
rather than a variety now, right?
Sorry?
That will be a scheme. It's not Artinian.
Well, if K
scheme rather than a
is,
variety, if I understand, right?
if I'm, if we're describing,
This
yeah, okay.
K
If
is
we start on,
multiplicity there.
if we start on a complex space, we'll get
yeah. So K will be the multiplicity.
That's right. That's right.
The devices,
That's right.
Yeah.
That's right. If I think about it as a hypersurface inside CP4, then, or some Derby version of CP4, then I can think about this as an honest Deline Mumford stack, and then it's that avoids the complexities associated with the origin. But I can also think about this just physically. I don't know that you care about the physics, but let me just put this off on the side. This is exactly U1 gauge theory with let's say 5 fields phi of charge K, and then one field, I describe this as one field P of charge minus 5K, and then some superpotential that looks like P times a polynomial times a homogeneous polynomial that basically describes the hypersurface. So where I was going with this is that this Derby version of the quintic is also a Z mod K gerb on an ordinary quintic, and the defining polynomial looks the same as the defining polynomial of a quintic. So for example, we could have phi 1 to the 5th plus and so on down to phi 5 to the 5th is equal to 0 would be a perfectly fine defining polynomial for this particular case, where the phi's all have weight K, so that this thing is now a degree 5K hypersurface. So that's what I mean when I say this is, if you drop the automorphisms, this projects down immediately to an ordinary quintic.
You have basically taken the coherent shifts like OK, etc. in the description of the space stack itself.
Sorry, say it again. You were breaking up slightly.
You have basically taken the coherent shifts like OK, etc. in the description of the space itself.
Right. That's right. So about the coherent sheaves, I had forgotten that you're also asking about the sheaves. So in terms of the sheaf theory, and again, I doubt I'm saying anything you don't already know. The sheaf theory is just, well, it's the sheaf theory on a gerb. So you've got basically sheaves that are pullbacks from the underlying space, which in this case is just P4, 5, and then you also have other stuff.
Yeah. So
the other stuff is going to be characterized by sheaves that look like sheaves that have a non-trivial action of that Z mod K in essence. So for example, so you could have on if I just work on that weighted projective stack PKK, then in addition to OK, which is some, let's say a pullback of O1, where pi is a projection from P4 K to K down to an ordinary P4, then you also have things like O1. And this also appears inside the physics as well. All of these get represented, and the difference just boils down to the action of that Z mod K. That's really what it comes down to. In terms of the decomposition story, I don't think we were asking about this, but let me just toss that in too. If I build the CFT of that particular Derby-Quinnic, so P4 K K with a hypersurface of degree 5K, that's basically going to be a disjoint union of 5 copies of the CFT of the ordinary Quinnic. And the 5 copies may have slightly different B fields. So the complexified Kähler parameters may be slightly different for the different quintics appearing inside here. But in other respects, it's basically a first approximation. The conformal field theory of that Derby-Quinnic is a disjoint union of conformal field theories of ordinary Quinnics.
Yep.
So I don't know if that answers your question. I think I've just confirmed.
Yeah, thank you. And, but this is related to the other comment that you made about probe brains, right? I mean, so these are going to see the probe brains are going to be these guys with this complexified Kähler.
Yeah.
Right?
Yeah. Yep,
So,
that's right. And the probe brains do some other fun things too. So for example, let me go to another page. So probe brains. So in the case of something like the orbifold C2 mod Z2, there's the probe brains do something else fun, which is the probe brains on a C2 mod Z2 basically look like they're basically skyscraper sheaves on, let's say, Z2 equivariant skyscraper sheaves on the cover C2. So basically, the probe brains basically looks like a pair of skyscraper sheaves. So at generic points in the C2, that's fine. That's going to map down to 1 point on C2 mod Z2. But then something funny happens over the origin. So there's a bit of extra physics that happens over the origin. And the extra physics is that at the origin, those probe brains can see non-reduced sheaves. So they see some non-reduced structure. And as a consequence, so physically what's going on is that at the origin, there's some, if it weren't for the Z2, if I had 2 brains that collided, there would be some gauge symmetry enhancement. If each of those skyscraper sheaves corresponds to a D brain with just a U1 gauge symmetry on its world volume, then when the brains collide, those U1s get enhanced to a U2. But then that Z2 kills off part of the U2, leaving you with a U1 cross U1, but the Z2 leaves behind a residue that consists of open strings, essentially nilpotent open strings. So that non-reduced structure corresponds to some nilpotent Higgs field. And then physically, when people do computations of the moduli space of brains, they're doing some computation of the moduli space of Higgs fields. And because you get some extra nilpotent possibility at the origin, what this means is that overall the probes see a resolution of C2 mod Z2. Basically due to the fact that at the origin, some extra non-reduced structure comes into play. So there was this old story. Probe brains are fun, but I often find their interpretation confusing. So another example, I think this ties into, someone had a question a few minutes ago about what other geometries, what other analogs of geometries can arise. So let me give a quick bit of advertising blurb for another notion, which is that of a non-commutative resolution. So there's an old notion of there's several notions of non-commutative geometry. There's there's nuts. I'm blanking. There's the original one by by Kansas. There's Kansas' original notion of non-commutative geometry. There also are various other notions of non-commutative geometry that pop up in different contexts. Seiberg and Witten had a picture of non-commutative geometry appearing in D-branes with B fields, which didn't seem to be very closely related to conses, but also resulted in some non-commutative rings. So, you know, there's that. There's another notion of non-commutative geometry that pops up that sort of revolves around the sheaf theory of a space, which is attributed to some combination of, I guess the particular application I have in mind is due to Kuznetsov, but he's really working with a notion that was introduced by Kontsevich and utilizes some work of a Dutch worker whose name I'm blanking on at the minute. Let me just say others, many others. There exists a notion of non-commutative resolutions, which for this discussion is defined by the sheaf theory. There exist closed string theories that appear to correspond to those non-commutative resolutions. So an example pops up as one phase in the gauge linear sigma model for a complete intersection of 4 quadrics in CP7. That phase, so it's a GLSM with a one-dimensional Kähler moduli space. The other phase describes a non-commutative resolution of a branched double cover of P3. So the P3 is basically the space of quadrics that's being described here. It's a singular branch double cover because ultimately for dimension reasons. But what appears physically is not the singular branch double cover, but a non-commutative resolution thereof. So this is another example of a something that's close to a geometry that pops up away from the singular points. The geometry looks like physics sees it as a branch double cover, but then there's something funny that happens at the singular point, which seems to naturally match the notion of a non-commutative resolution that it pops up in works of these authors. So if you look at D-brane probes here see a resolution of that singular branch double cover. And in fact, the resolution they see, the resolution they see is not actually Kähler, which is strange to understand. Recently, Thorsten Szymanek has been looking closely at this and has an idea, which I think he's got a good justification for, which is that these non-commutative resolutions, or at least this particular non-commutative resolution, is really a blowdown limit of, indeed, that non-Kähler space, but with a non-trivial B field on the cycles that are shrinking. So this, I've been talking to Thorsten a great deal about this recently, and I think he's really onto something, but it's still sort of early days for his picture. One of the I think one of the questions in my mind about this physical realization of non-commutative resolutions is they pop up in a very haphazard fashion. There are a handful of examples that people can do computations in which they look at a phase and they realize that phase can be interpreted in this fashion. But if you just said, okay, here's a singular space, how do you describe the CFT for a non-commutative resolution? I would have shrugged my shoulders. I don't really know. I don't know how to give an a priori construction of a closed string theory for a non-commutative resolution. But Thorsten's work and the way Thorsten's idea suggests that it is possible. In fact, suggests a mechanism by which one may be able to compute, by which one may be able to construct closed string theories for non-commutative resolutions. Anyway, sorry, this is all pretty far afield, but there was a question. Someone made some statement about it's fun to consider things that are almost geometries. How far can you push conformal field theories?
But on the other hand, all of this seem to be basically a redubbing of the complexification of the Kähler potential.
Sorry, say it again. They're all basically a
redubbing of the complexified Kähler potential.
Yeah, I guess so in some sense.
Yeah.
And these
perhaps more rigorous too, but
Yeah, but I think that's, I mean, it's a recent development, but I think Thorsten's work in this context is definitely pushing towards that direction. If I understand where you're driving at, I think Thorsten's argument is that these non-commutative resolutions are what you get basically if you have granted some non-Kähler, some sigma model on some non-Kähler space, but with some suitable B field, and you take some blowdown limit. I can indeed imagine a physical construction where I take some UV theory that is not itself a superconformal field theory, but which flows to a superconformal field theory, and you adjust parameters so it flows to, so that you basically follow along some path with some non-trivial B fields. You end up with a theory with a frozen B field stuck at the blowdown limit. So that makes sense from indeed from the extended Kähler moduli space perspective. Before Thurston's
because
work,
otherwise, if I blew it down, I wouldn't see anything, right? I mean, I could just no obstruction to blowing down the exceptional devices. So if there was no B field at all, I mean, so.
That's right. So part of what seems to make these examples work is that the B field that's being, the B field on the exceptional visors is topologically non-trivial, so that there's some sense in which you can't get rid of it. So then when you blow it down, you really can't just rotate it away. It's really genuinely, you're really stuck with it, and that's why it's popping up. That's why it's sort of sticking out notably in examples like this. It's because it's, I mean, it's the blowdown of a topologically non-trivial B field. So you really can't. I mean, you're really stuck. You really can't get rid of it in any fashion.
Yeah. Thank you for all these explanations.
It's my pleasure. Thank you for the excellent questions. This has been a lot of fun.
Excellent. Yeah. Okay. So yeah, have a good day.
Okay, you too.
Yeah. Thanks a lot. Yeah. Are there any more questions, or maybe it's already late for you? Yeah, okay. Like, if there's no other question, maybe I can ask you another thing, which is that.
Sure.
Yeah, also something that I was wondering, but I'm not a mathematician myself, but I'm interested in this, so
okay.
Let me ask. But the question is, so yeah, for example, we know how to define, like, say, string theory on, let's say, the quantic, so algebraic varieties, for example. Like, I was wondering how much is known or how difficult it is if we want to do this kind of construction, but for more general algebraic varieties, so let's say not over C, but over like a general field.
Oh, I don't have a clue.
It's just too difficult.
People have thought about this. I don't know. So there's some history behind this. So for way back when, there was Peter Freund, am I remembering his name correctly, at the University of Chicago, who thought a lot way back in the late 80s about string theories over other fields. So the questions he was asking, at some level, the questions he was asking even go back to just very basic statements about scattering amplitudes. The prototype for a string scattering amplitude is basically a ratio of gamma functions, and one can define gamma functions in somewhat greater generality. And he used that as a starting point to try to think about how one could make sense of string theory over other fields. And this was before my time, so I have just very much an outsider's picture of what work went on. I vaguely recall that what came out of that at some point was a review article that summarized. Well, one of the first questions you could ask was, what's the world sheet theory? How do you build a world sheet theory over finite fields that duplicates those particular scattering amplitudes? And my vague recollection is that there were multiple different answers. And at least from the outside, it wasn't clear what the best, it wasn't clear to me what the optimum strategy would be. But other people have used it. I know Ashok Sen had some papers way back when he worked over finite fields and used that as a kind of regularization method. I know Philip Candelas and Xenia de la Osa have looked at sort of general properties of calabi-Yals over finite fields. They've asked questions about, I think they're motivated by mirror symmetry. They've asked questions like, how do you, what partition functions can you compute? What is a partition function over a calabi-Yal over a finite field? How does are there any parallels between the number theory there and the physics of that geometry. What analogies can one draw? How can you push that? You know, and I get the impression that some other people have tried thinking about that since. I don't know. You know, various people have thought about it. I don't have. All I can really say is various people have thought about it, and it seems like it would be interesting to do. And I'm not certain what the, you know, people have thought about it. I'm not certain what the optimum you know, strategy for really getting into it. I suspect that the answer might depend upon what it is that you want to do. I mean,
but shouldn't it be something very general, like just like the definition of a scheme, for example? Shouldn't it only depend on the ring?
It's a net. Speaking very naively, I completely agree. It seems like there ought to be, speaking very naively, some very general statement one ought to be able to make.
But yes, I guess in
maybe the problem is just that. Yeah. Maybe the problem is just that sometimes the problem is just a matter of finding the right definition. You know, my very limited understanding of the results that came out of Freund's old work was that there were many possible approaches, and it wasn't clear back then which is the right one. My sense from what Philip Candelas and Xenia Delosa have been doing is that they're sort of trying to adopt a more phenomenological approach. They've been doing lots of computations, trying to find some parallels with physics, but they haven't really taken a first principles approach of let's try to define a quantum field theory over a number field and then see what that gives us. Yeah, it seems like it would be very interesting to do. I would not be surprised if there's quite a lot that could be said. I mean, in principle, if you worked over a number field, that would, you know, naively, that would seem to avoid a lot of the usual difficulties of quantum field theory. You know, usually the headache, I'm sure I'm speaking to the choir here, the headache in making sense of continuum quantum field theory is the continuum. It's ultimately the reason for regularization, renormalization, and all of that. If we were working over a finite field, naively, all of that could go by the wayside and a path integral would reduce to just a finite sum. I mean, it seems like there ought to be just a simple general
I guess one thing
can I make a comment on this?
Oh, please do.
Yeah.
I'm just speculating.
So actually, there's a slight problem with this p-adic, especially this p-adic fields. The biggest problem is in doing or when the OPs is when you write OPs etc. in any quantum field theory. So these are ultrametric fields, and this all triangles are isosceles triangles, right?
Okay.
And so that essentially means that it's kind of after a 3-point function, it becomes kind of trivial. So that makes any progress very difficult there. This that's how I think late 80s had some papers in as a very famous paper on the
but over number field it won't be ultrametric, right? So this is only for the p-adic case.
Yeah. So wherever all triangles are isosceles triangles, this problem is there. After 3 points, it's kind of there's nothing to stay.
I was not thinking actually of a Q or Z or even, you know, but okay.
Yeah, that is a problem there. Typically, that's the biggest problem there.
No, but I'm not asking about p-adic fields, I guess. Yeah, okay.
Anyway, clearly people have thought about it. I have not thought about it in any depth, but it's you know, I agree with the spirit of the question that it seems very naively, it seems like it ought to be possible to say something, but as was just pointed out, there could be technical difficulties, and I
for sure, probably, I guess something that I find difficult to think about is in continuum quantum field theory, the notion of like differentiation is very important, right? Like,
so I mean, certainly you could replace derivatives with
differentiation exists there. That's not a problem. There is a notion of something called Vladimirov derivative there.
But even over finite fields?
This is called something called Vladimirov derivative.
But even over finite field, or?
Yeah.
I guess even over number fields, I guess there's a notion of a derivation. There's a notion of tangent vectors.
Yeah, that is not a problem. The essential problem is in the fact that for any 3 points, two of them are equally
Yeah,
separate.
but so you said that this was only for the periodic field. So if I
No,
just
these
look
are
at
for ultrametric theories where all kinds of local fields.
yeah, but if it's
ultrametric,
okay,
if it's
or
ultrametric.
maybe I don't understand something. But if I just look at, if I just want to do a standard number field, like an extension of Q or whatever.
The problem is the closure of the field. You have to have a closed field.
Okay, let's say the algebraic closure of Q.
Typically, that's the only extension that you have out of Q, right? QPs are the periodic field. Right?
Oh.
There's a theorem for that. That's only sort of.
Why can't I just do? Why can't I just do two bar like the closure of Q?
Okay, I don't know the answer, but I think there'll be some. It will not be much different from C, etc. So just Q bar may not work.
Yeah, for sure. I may not work. Yeah, I'm not saying it works. Yeah, I'm just saying it.
Yeah, so instead
QP is
very good. QP or all kinds of local fields with extensions are very good examples, but on the other hand, they have this difficulty.
Okay. Thank you. I see what you mean.
But this review that Eric referred to, Brekke and Freund, this had some of the old results, and it's nice.
Which review?
This is a physics report. So this is the one Eric was referring to, I guess. Brekke and Freund.
The old Freund review article.
Yeah, Brekke and Freund. BREKKE, Brekke and Freund. It's a physics report, I think.
Okay.
Yeah.
I should go back and take another look at that.
That's very interesting. I mean, so this question itself is very interesting, but yeah, I also couldn't do anything. I tried to do a little bit, not much can be done.
Well, I apologize for not mentioning you. I'm very much an outsider to the field. I just
no. So don't worry. Yeah.
I see. Okay. Yeah, I'm also an outsider of the field. I mean, I remember when I was at PITP, I asked this question to Wang-Wen-Witten, and he told me that he thinks that it's not a good research direction to go because it's too hard. But okay.
You might be right. Yeah.
Yeah. Okay. Now I'll have to leave. So it was very nice having this discussion with you.
Thank you very much. You had some great questions. It's been a lot of fun.
Yeah.
Thanks a lot.
Thanks a lot. Thanks a lot, Eric. It's a wonderful talk, and for staying so long.
That's my pleasure.
Thank you. Right. So let me end the talk now. Thank you.
Have a good day.
Have a good day.
All right.
Bye.
Bye.